Right. Well, thanks a lot. Thanks a lot for the invitation. I'm very excited to be here and hear about all the work that's going on as part of this project. So I'm going to talk about multi-decadal variability in the North Atlantic jet stream and its connection to sea surface temperatures, and I'll talk a bit about some of the implications for predictability. So there's a number of recent studies that have argued that global climate models underestimate multi-decadal variability in the North Atlantic jet stream. And so each of these studies I've listed here they've argued that using the wintertime average North Atlantic oscillation variability. And so I just kind of started looking at this a little bit by accident as I was evaluating the new CESM model. And I was having to do it on a monthly basis, looking at jet stream metrics, and realized that if you look within the winter season on a more monthly basis, there's actually quite big differences across the season in terms of the multi-decadal variability that's present. So I'm just going to start with a more simple measure of jet stream variability than the NAO, although it's highly correlated with the NAO, but it's more general than the NAO. And that's just taking 700 hectopascal zonal wind, and then at each grid point, taking the time series for a given month or a given seasonal average. So for example, if I'm showing January, I just take all the Januaries together and string them together in a time series, and then calculate the 20-year running mean of that time series, and then calculate its standard deviation. So that'll just give a measure at each grid point in the North Atlantic domain here of the variability in 20-year climatologies over the course of the record. So here I'm showing that this is for the wintertime average from December to March, and this is for ERA 20 C reanalysis. I'm going to vary the exact time period I'm using, but that doesn't matter too much. I'm just going to be consistent between the models and the observations. And so this is obviously a reanalysis product that's being constrained by surface pressure observations and marine surface winds. And then this is what it looks like in the NCAR model. So this is a CSM large ensemble. This is a large ensemble of 40 coupled historical simulations with CESM. And then this is the difference between them. And so the gray regions here are regions where the reanalysis lies within the spread of the 40 members. So that's where the model is behaving reasonably. And then in these yellow regions, these yellow regions here, that's where there's more variability in the reanalysis on these 20-year timescales than what you capture in any of the individual large ensemble members. So that's telling us that we have a problem and there's more variability in the observational record than we have in our model, which is consistent with those other studies. But then if you break it down and look at the individual winter months, what you see is that there's progressively more multi-decadal variability in the jet stream toward the late winter. So it's really much bigger in March. And it really maximizes in March. So here I've just taken an average over this North Atlantic box of this 20-year running means. And instead of using monthly values, just use 31-day running means over the course of the year so you can see the full seasonal cycle. And you can see that the multi-decadal variability is really large in March and late February. And here I'm just showing a time series again in this North Atlantic box. I'm going to use this box a lot. And now here I'm showing all the other reanalysis products. And so you can see that where they overlap, there's pretty good agreement between them. And in March, you can just see this low frequency variability in the winds without doing any kind of filtering. That's what it looks like in the large ensemble, and then this is the difference between them. And so what you see is that the discrepancy between the model and the reanalysis is much larger in the late winter. So in March, and to a lesser extent in February, there's much more multi-decadal variability in our observed record than what we capture with our model simulations. So that's one model. What about other models? So here I'm showing the same measure, multi-decadal variability in the winds in March, 20-year running means, and the standard deviation of that. And now I'm showing all of the coupled CMIP5 historical simulations, and these black lines are the reanalyses. So these are all actually behaving like CESM, and none of them come close to the degree of multi-decadal variability that we've seen in our observed records. So CSM is typical of models, and they all seem to have less variability than what we've observed. So far I've just shown you 20-year running means. We could ask, how does this depend on the time scale? So here I'm just showing that as a function of the number of years in the running mean going, so this is again just for March, from interannual variability out to 40-year running means. And so here are the two 20th century reanalyses. And each of these red points are an individual member of the CESM large ensemble. And so what you see is that on the high frequencies from interannual down to maybe 5 or 6 year running means, that reanalysis lies within the spread of the model distribution. It's hard to conclude that there's anything wrong necessarily on the high frequencies, but once you get out to decadal or 20-year running means, it becomes clear that what we've observed is outside of what our model is capturing. So I just want to mention what the implications of this variability are. So here again, I'm just showing that time series of winds in this North Atlantic box. And I'm going to show the jet stream climatology for two 31-year periods for March. So this is March for the 31-year period centered on 1995, and then this is centered on 1950. And so there's a pretty drastic difference, even with the 31-year climatology in March, between these two periods. And then you can see the implications of this for precipitation. So here, this is station-based precipitation observations, so very independent from the reanalysis. And what you see is that back in the later decades, centered on 1995, when the jet stream was strongly tilted and guiding the storms toward the UK, Scotland is characterized by a far greater precipitation climatology than the Iberian Peninsula. But if you look at a 31-year period for March, again, back centered on 1950, the jet stream in this period was much more zonal, instead guiding the storms toward the Iberian Peninsula. And Scotland and the Iberian Peninsula for this 31-year period were characterized by rather similar precipitation climatologies, which is not at all the view that we have from the more recent decades of these two climates. So one question that always came up when I talked about this before, just looking at the reanalysis jet stream variability, is really, can we trust the representation of the reanalysis? So, or the representation of the variability in the reanalysis. We can see that all the reanalyses kind of agree, but they're all being constrained by the same observations. Is there some kind of inhomogeneity being introduced because of the different number of observations or the way the observations are being done? But this link with precipitation allows us to really verify that the variability in the reanalysis is real. So I'm going to reconstruct the variability in the jet stream using precipitation observations, and just start by considering interannual variability over the satellite era record. So from 1979 onwards, when we're a bit more confident that things are observationally constrained. And so here I'm just showing the regression of 700 hectopascal zonal wind onto winds in this North Atlantic box in March, interannually, for the satellite era record. And here I'm using era interim, which is more observationally constrained than the era 20 reanalysis, era 20C reanalysis. This is the equivalent regression, so interannual regression of precipitation onto winds in this North Atlantic box in March for the satellite era record. This is using station-based through precipitation observations. And so what you see is that interannually, when you have stronger westerly winds to the west of the UK, you got more precipitation over Scotland and less over the Iberian Peninsula. So that's not too surprising. So we can just take an index of precipitation as the difference between this Scotland box and this Portugal box. And that will be related to the variability in the winds in the North Atlantic here. So this is just the interannual relationship between winds in the North Atlantic and this precipitation index. And you can just fit a linear regression using this interannual variability over the satellite era record. So now we can take that regression and ask, can we reconstruct the low frequency variability in the winds going further back in time if we use completely independent precipitation observations? So here I'll show the reconstruction. So this is for March. This is the winds in the North Atlantic, and the left is the annual values, and the right is the 20-year running means. And I'm just showing the satellite era record here so far where we fit that regression. So in red here is the reconstruction that you get using the precipitation observation. So it works pretty well. On high frequencies, obviously there's noise where these two things are not related, but on low frequencies, it works pretty well. But of course, we fit the regression model over this period. The real test is if we then take our precip going back to 1900, can we reconstruct the low frequency variability in the winds? And so this is what we get. So you can pretty much perfectly reconstruct the low frequency variability in the reanalysis winds using precipitation observations, which are completely independent. So that gives us confidence that this low frequency variability really happened. So then the question is, what caused this low frequency variability in the jet stream in March? And so there are a number of possibilities to consider. So one is it could just be the chance sampling of higher frequency noise. Maybe we don't need to invoke any kind of underlying forcing to explain it. You just randomly sampled months where the weather has been different, strung them together, and got some apparent low frequency variability. It could be due to internal coupled ocean atmosphere processes, so the longer time scales in the ocean circulation could be imparting some low frequency variability onto the atmosphere, or it could be due to external forcings. So if we were to consider the first of these, if it was just due to the chance sampling of higher frequency noise, then if we want to explain the difference between the model and the reanalysis, either the model would have to be deficient in its representation of the high frequency variability, but I've already shown that for CESM, and it's true for other models, that on the high frequencies, it's hard to say there's really a problem in the models. They look pretty good. Or the other possibility is that what has happened in the observations was just a very unlikely occurrence. So we could ask, well, how likely is it if we were to just suppose the variability in the winds was just a random Gaussian white noise process with a standard deviation equal to the interannual standard deviation, how likely is it that you could obtain that degree of low frequency variability that we've observed? So we can just generate many synthetic Gaussian white noise time series and ask that question. So I'm just going back, this is the plot I showed at the beginning of the standard deviation of 20-year running means in the reanalysis and in the model. And I'm just going to add on gray shading, which is going to show regions where this variability is not larger than what you'd expect to arise from just the sampling of the Gaussian white noise process at the 95% level. So what you see here is that the model is just, it's entirely indistinguishable from white noise. You don't need to invoke any underlying low frequency forcing to explain any of the low frequency jet stream variability that we see in our model. The same is true over the North Atlantic Ocean in the early winter, but then in March, the variability that we've observed really is well outside of what you could expect to arise from the sampling of just a white noise process. The same is true if you fit a red noise process. There's not very much autocorrelation from one year to the next. And so in this region here, for a white noise process, the chance of obtaining that degree of variability is only a 0.04% chance. So even if you're take into account the fact that I've done multiple tests here, it's still very unlikely that you could obtain this degree of low frequency variability just from the sampling of white noise. So I think it's certainly possible that just random atmospheric noise has contributed to what we've seen, but I think it's sufficiently unlikely that that's all that's going on, that we can be motivated to try and understand is there another underlying low frequency cause. And so then we have these two possibilities: internal coupled ocean atmosphere processes or external forcings. So first, I'll search for a link with sea surface temperature variability. So if we just take our time series of winds in March in this North Atlantic box and take the 20-year running mean, and now I'll correlate that with sea surface temperatures globally, and this is what you get. And so obviously we have very few degrees of freedom here. We have like just over a century of record, and we're looking at 20-year running means. All the statistics are very marginal. But the stippling here is showing regions where the correlation is significant at the 95% level using a test that tries to account for the lack of degrees of freedom. So what you see is that there's a strong negative correlation with SSTs in the subpolar gyre region of the North Atlantic, and then a positive correlation in the Southern Ocean. And this looks very much what you pick up with traditional AMV or Atlantic multi-decadal variability indices on these 20-year timescales. So the AMV, it's typically defined by taking an area average in this North Atlantic box of sea surface temperatures. And then you use some kind of method to isolate the internal component of the variability from the externally forced contribution. And then there's been a lot of debate in the literature recently over the relative roles of the ocean circulation and then the direct forcing of the atmosphere on the ocean mixed layer and giving rise to whatever you pick up with in this index. And I think really both play a role. And I just want to be clear about exactly what I'm talking about on these 20-year running mean timescales, because often people say, well, that's not the AMV that you're looking at. So this is what the pattern of SST variability that you pick up with this index. This is using the Trenberth and Shea method, but I'll get back to that in a second, on different timescales. So interannually, you see this horseshoe pattern. And on these timescales, this was argued by Amy Clement to be primarily produced by wind forcing on the ocean mixed layer with not much of a role for the ocean circulation. Then as you go to 10-year running means, and this is a typical timescale used to define the AMV or the AMO, that southern lobe of the horseshoe becomes weaker, but it's still there. And then when you look on 20-year running means, which is the timescales I'm talking about, the SST anomalies are pretty localized in the subpolar gyre region of the North Atlantic. And there's not so much of a horseshoe, and this pattern was argued to be very much associated with changes in the ocean circulation. And I'll argue that in a second as well. So it's the AMV that you pick up with this Atlantic average on these 20-year timescales is what I'm talking about here. And this pattern looks very much like the correlation pattern that we have between the winds and the SSTs. So I'm going to show 3 different AMV indices. One is the Trenberth and Shea, where you just subtract the near global average, so from 60 south to 60 north, with the intent of trying to remove the externally forced signal that comes along with a global change in SSTs. The second is this one by Claude Franquignol that was introduced recently in this paper, where they basically use a linear inverse model to try and pull out the externally forced contribution from the internal variability. And I can't really speak to the details of how this is done. I just basically got their index from them. But this paper looks into all these different indices in large ensembles where you know the answer because you know what the externally forced contribution is. And they argued that this method works the best to isolate the internal variability, but they also argued that this method works pretty well in the North Atlantic as well. And then the third one I'll show is where you just subtract a linear trend, and that's not because that's a good way to remove all the externally forced component, but these papers argued that there's an important role for aerosol forcing in the AMV that's been seen, and they argued that using this linearly detrended index. So I'm going to show all 3 of those. So here's the correlation between the winds in the North Atlantic box and the AMV using the Trenberth and Shea AMV on these 20-year running mean timescales. And so what you see is there's a really strong negative correlation between the winds in the AMV in March. It's much stronger than you see in any of the other winter months, and it's stronger than what you see in the winter season as a whole. And if you were to just look at DJF, you might miss this altogether. It's still there if you go further back, so you might question, well, do we trust the observations? But if you go back to 1854 using 20th century reanalysis, the picture doesn't change. It's not dependent on the SST data set that you use. These are 3 different SST data sets. This is what it looks like with the Franquignol et al. Lim optimal AMV index. And so there's similarly high negative correlation, but there's just not quite enough degrees of freedom for it to be passing the significance test. And then this is what it looks like with the linearly detrended AMV index. So that's pretty different. So this index was argued to retain some of the aerosol force component, and it's not correlated with that index. It's correlated with the ones that have been argued to retain only the internal variability, if they're working correctly. So I can understand if you're skeptical because we have very few degrees of freedom. I just want to put up the full time series. So here I'm going back to 1854 using 20th century reanalysis. The black is -1 times the AMV, and the red is the winds in the North Atlantic. And so on high frequencies, there's all sorts of noise where these 2 things are not related. But on low frequencies, hopefully you're convinced that there's a pretty high correlation between these things. So the month of the winter where we seem to have this low frequency variability in the jet stream that we really need something to explain it is the month where we have a strong correlation with the AMV. So at least from this correlation analysis alone, SSTs have the potential to be a driving force for that jet stream variability that we've seen. We know that coupled models tend to underestimate the AMV. There's been a couple of recent studies that have shown that. And so we could ask, well, do we do better if instead of using the coupled models, we prescribe the observed SSTs so that we have the realistic SST variability? So I'm going back to this plot I showed earlier, which is showing all, this is again the standard deviation of 20-year running means in this North Atlantic box in March. And these were all of the coupled historical CMIP5 simulations. In gray here, I've just added the range of what you could expect to arise from white noise sampling using the observed standard deviation. And so all the models are indistinguishable from white noise as well. And these black points now are two 10-member ensembles with prescribed observed historical SSTs. So one is with CESM and one is with the ECMWF model. And so these look just the same as the coupled models. There's no indication that we do any better if we prescribe the observed SSTs. So there are indications that the SST variability could be a driver, and maybe models are deficient in their representation of this connection. But obviously, from correlation analysis alone, how do we know that that's what's going on? I'm arguing that there's something about this SST variability that's driving the variability in the winds, but we have many studies that have shown the importance of the winds in driving the SST variability itself. So how can we be confident that this correlation we're seeing is not simply an influence of the winds on the SSTs, and rather is something the other way around? So there are kind of a number of arguments that not all of them are perfect that you could make. Combined, they all point in that direction. And I want to just show the one that I think is the best. And that comes from the behavior of decadal prediction experiments. So there's a decadal prediction large ensemble that's been performed with CESM. And these are initialized decadal predictions with observation-based ocean and sea ice states. So first what's done is there's a forced ocean sea ice simulation, or FOSSI, is run, where just the ocean and the sea ice models are run with, they're forced by observed surface fluxes. So that gives you an observation-based state of the ocean and the sea ice models. And then from each November of each year of the simulation, from 1954 to 2017, 40 members are initialized. They all have the same ocean state and sea ice state from this FOSSI run. They're all given a different atmospheric state that's taken from the uninitialized large ensemble. And so these are 40 simulations run for 10 years under historical forcings, all initialized with observation-based ocean and sea ice states. And so this here is showing the prediction for SSTs in this subpolar gyre region of the North Atlantic at 10-year lead time. So the black is observed SSTs, and the red is the ensemble mean prediction for SSTs 10 years after initialization. So what you can see is that these are able to predict the low frequency variability in the SSTs in this region 10 years ahead of time. In contrast, this is the prediction for the winds in this region of the North Atlantic at shorter lead time. This is at a 5-year lead time, but the same is true for any lead time. Basically, the model has no skill in predicting the winds in this region in March. So what we're seeing here is that the initialized predictions can predict the SSTs without predicting the winds. And so they don't need the winds to directly be driving the SSTs. Rather, there's something in the initialization state that's telling the model where it's going to go for the next 10 years. And so if we just look at the uninitialized large ensembles where the only predictability is coming from external forcings, that doesn't capture either of these things. So what the decadal prediction large ensemble tells us is that the initialized model can predict the SSTs at 10-year lead time without predicting the winds. So the SST variability is not just a result of the direct influence of the winds on the ocean mix layer. There is definitely a role for the ocean circulation in this low frequency variability. And it's the initialization of the ocean and the sea ice states that's leading to that predictability. So it's not a direct argument showing the SSTs are driving the winds, but it's an argument that's showing that the winds are not directly driving the SSTs. Therefore, there's no reason to expect them to be so highly correlated unless the SSTs were influencing the winds. And I just want to mention a bit about what can we say about the role of the internal versus externally forced contribution, because my feeling is that this is all internal variability, but the arguments to get there are a little bit convoluted, and I can definitely see that arguments could be made that external forcings are playing an important role. So I would just want to outline all the arguments that make me think it's largely internal variability. So one is that the correlation between the winds and the AMV is with the AMV indices that have been designed to retain only the internal variability. That's been argued in this Frank-Ignoul et al. Paper that they work well in the context of large ensembles. It's conceivable that the real world is sufficiently different from the models that maybe they don't work well in the real world, and I could accept that that could be the case. I think at this point we don't really have reason to believe that. It's difficult to find a combination of forcings that gives the right phasing and frequencies over the course of the century. All I've done to look at this, though, is considered global forcings. Maybe you could do better. You could come up with local aerosol forcings in different regions, perhaps combining to give us that low frequency variability. And then even if external forcings were responsible, I think they have to be acting through the SSTs. So I don't think it can just be the external forcings driving both the SSTs and the jet stream separately, because then it would be hard to explain the behavior of the decadal predictions, because they know what the SSTs are going to do 10 years ahead of time, 10 years before the winds do. So if there was an external forcing that was acting on both, it would be hard to explain that. I think it would be easier to say, well, the external forcings are driving the SSTs, which are then influencing the winds. So for me, all this is pointing towards internal variability being the dominant thing that's going on here. But I guess I'm hoping to learn more about this later today. So my hypothesis then is that the low frequency variability in the late winter jet stream is being forced by internal variability in the SSTs, which is associated with variability in the ocean circulation. Of course, the winds could then be feeding back onto the SSTs. We know that winds are an important driver of AMV, but normally we think of it as being a lead-lag relationship. So the winds change and the AMV changes, but in March what we see is an instantaneous connection between the AMV and the winds. And I think what's going on is the AMV is largely driving the wind variability. This is consistent with some other observational studies that have argued the positive phase of the AMV is accompanied by a negative NAO in the wintertime average. I'm arguing that this connection is stronger in March than what you get in the wintertime as a whole. And you also see some more things if you don't restrict yourself to the NAO, although my wind index is very highly correlated with the NAO. Modeling studies, I think they don't always agree on whether there's a robust response to the AMV, but more often than not, it's in the sense that the positive AMV gives you a negative NAO, which is consistent with what we're seeing in the observational record, but typically I think it's of small magnitude, and I think there's really something wrong with our models, that they're not capturing this connection correctly. So this would be much more convincing if we could understand the mechanisms, and I have failed to do that so far. So it's really difficult because no model does it. So it's hard to look at in models. And if you want to look at it in observations, you kind of have to go back to the 50s, where maybe we're not so confident in the observational constraint on other aspects, like if you want to start looking at the divergent circulation in the tropics and things. I'm not sure how confident we are. There's maybe more that could be done. For example, we could look at analysis increments and see if there's something that we could look at over the satellite era record to try and get at what's going on. Arguments have been made for a stratospheric pathway. I don't think it's that. The magnitudes don't add up. I would be happy to talk about that afterwards. It could be anything about this pattern of SST variability. It doesn't have to be local to the North Atlantic, although I think it's much more likely that it is local to the North Atlantic. And then why March? It's an obvious question. Could that help us somehow to understand the mechanisms? I'm not sure that there has to be anything really special about March. Here I'm just showing the regression of 20-year running mean winds onto the AMV. And there's kind of hints that you have a similar pattern earlier in the winter from January, kind of building into February and then really maximizing in March. So it could just be that there's some process that's forcing the jet stream continually over the winter, and then some with the various eddy feedbacks and things that kick in, it maybe just takes time for it to build up, but without really understanding the mechanisms, it's really speculation. An obvious question is, does resolution help? There are various reasons why we might expect low resolution models to not be capturing the ocean atmosphere interactions correctly. So far, I've looked in the Primavera simulations. The highest resolution models are 1/4 degree atmosphere, and I believe they're using 1/4 degree prescribed SSTs. I just looked at the prescribed SST runs, and they don't look any different from the low resolution models. So if it is resolution, it's beyond what we do right now. I guess I have one more hope, and that is that there's going to be a high resolution decadal prediction run with a 1/4 degree atmosphere and 10th degree ocean, which will be coupled, and it will have a higher resolution open ocean. Maybe that will show something. So I just want to finish up by talking a bit about the predictability of precipitation based on this. So I've argued here, I'm just showing the regressions of 20-year running means onto the AMV, that when you have the positive phase of the AMV, when you have warm SSTs in the subpolar gyre region of the North Atlantic, you have reduced westerly winds to the west of the UK, basically an equatorward shifting of the jet stream. You have reduced precipitation over the UK and increased precipitation over the Iberian Peninsula. So possibly there could be predictability on decadal timescales, and our models capture, they can predict the SSTs in the region of relevance, but they don't capture the connection with the winds or with the precipitation, which I'll show in a second. But I want to suggest that maybe we can bypass that and just use the model predicted SSTs and then the observed empirical relationship between the SSTs and precipitation to come up with some skillful predictions for precipitation in Western Europe on the decadal timescale. So I'm going to use for the model predicted SSTs, I'll use those from the CSM decadal prediction large ensemble that I've already mentioned. So I'm going to try and predict precipitation for the UK, Western UK, and Portugal. And this is all going to be on decadal averages, because this is what we have from the decadal prediction large ensemble. So this is the correlation between decadal average SST and precipitation in these regions. So basically, when you have warm SSTs in the subpolar gyre, you have reduced precip over the UK and increased precip over Portugal. Now here's the scale of the decadal average SST predictions in the decadal prediction large ensemble. So we have pretty high scale over much of the North Atlantic. And so I'm going to take an index of SSTs as being the difference between this north box and this southern box. I've chosen this obviously because it's one that works very well, but it's not the best, and it's pretty insensitive as long as you have something that encompasses the subpolar North Atlantic. So here's what that index looks like. Black is observed, and then the red is the predictions for the forthcoming decades. So we can skillfully predict the low frequency variability with the initialized predictions. So we can use the observation-based relationship between the SSTs and precipitation on decadal averages. So I'll just find these A and B coefficients using the full observational record, and then plug in the model predicted SSTs to see, can we skillfully predict precipitation in March for the forthcoming decade. And I'll show two measures of skill, the anomaly correlation coefficient and the mean squared skill score. Basically close to 1 is good. So on the top, I'm going to show the predictions for the UK, and the bottom is for Portugal. And here's the decadal average precipitation. This is CRU precipitation observations. Here I'll show the anomaly correlation coefficient, and here the mean squared skill score. So this blue line here is what you get from the uninitialized large ensemble. So this is the prediction from the model, where all the model is given is external forcings. So there's no skill there. The blue line here is the prediction from the initialized large ensemble. So this is what the model gives you if you initialize the ocean and the sea ice, and it also has external forcings. And again, there's not a lot of skill there. And then in red here, this is the prediction that we get if instead we use our model predicted SSTs and the observed relationship between the SSTs and precipitation. And so now we have some pretty high skill. Obviously, we don't have a very long record for kind of validation of these forecasts. The error bars are pretty large, so the mean squared skill score in Portugal is not significant, but it's still relatively high. In green here, this is what you get if you just plug in the observed SSTs. So this is what you'd get if you could perfectly predict SSTs in advance. And so the skill is higher, but it's not that much higher. Now you might be worried, is this all just a case of overfitting? Because obviously I've used a full observational record to derive the relationship between the SSTs and precipitation. In the asterisks here, I'm showing what you get if instead you use the period up to when the decadal prediction large ensemble begins to derive those regression coefficients and then predict the remainder. And so you have similarly high skill. The error bars are much larger. I'm not showing that here because there's much more uncertainty on the regression coefficients. But it still works if you use a kind of cross-validation procedure. So now here's the predictions for the next 10 years. So the prediction is that the UK in March will be a little wetter than it was in the early 2000s, but not as wet as it was in the 80s and 90s, and then vice versa for Portugal. So we can see in 10 years' time whether that's actually worked. Okay, so to conclude, there's pronounced multi-decadal variability in the North Atlantic jet stream and precipitation in the late winter. March in particular is kind of the key month. The precipitation observations, they provide a completely independent quantitative verification of the jet stream variability that we see in the analysis products. The variability seems to be strongly connected to SST variability in the North Atlantic in the form of what you pick up with traditional AMV indices on these timescales. And so the hypothesis is that what we're seeing is some internal coupled ocean atmosphere variability. So internal variability in the SSTs involving the ocean circulation is somehow driving the variability in the jet stream, and our models are not capturing this process correctly. The SST variability seems to be predictable, so there's potential predictability of late winter precipitation in Western Europe. This is limited to March, so I don't know whether it actually has any use, but apparently March is kind of important for Portuguese wine, so maybe there's some use. But I think if we could have an improved understanding of the mechanisms behind this, what's going on in the real world, why our models aren't capturing it, then that would give us a lot more confidence in those predictions. And so this is out in a couple of papers. All the wind variability is in this one, and then the precipitation one came out last week. So with that, thanks again for having me, and be happy to take any questions.
Very much, Isla, and we've got 5 minutes for questions, and remember, we'll need to repeat them for people online. Okay. Yeah.
I was also wondering what is special about March. And in the ocean, March is when the mixed layer is deepest, so the atmosphere will connect to the deeper water masses in the ocean. So if you're driving variability is coming from the ocean on multi-decadal timescales, must be coming from fairly deep down in the ocean, deeper than the mixed layer, deeper than the surface layer, which is sort of what you'd expect on the longer time scale. So I wonder whether you thought about that in any detail.
Okay, so the question is whether there's a role for the deeper mixed layer in March, which would allow the atmosphere to feel the ocean deeper down. Yeah, it's definitely a possibility. I guess there's not that much. If you could do the same correlation analysis with the February or the January SSTs, and you would see the same thing, and the SSTs don't vary that much. But yeah, that could be playing a role. I haven't looked into it.
Okay, Simon.
Yeah, I've got one about the heat exchange. So you showed your chicken and egg a couple of times, and I wondered if you looked at the net heat exchange as an additional source of information, because the relative sign of the anomaly in the heat exchange and the anomaly in the SST enables you to establish that direction between the chicken and the egg, whether the atmosphere is forcing the ocean or vice versa.
Yeah.
Have you explored that very much?
Yeah, so the question was whether I looked at the sign of the surface fluxes to determine the causality, whether the ocean is driving the atmosphere or vice versa. And yeah, I have looked at that. I guess Mark Kane has recently argued that that doesn't necessarily tell you the direction of causality, but I looked at it anyway. And if you look like, yeah, over much of the region, it's in the sense of the going into the ocean, but that's not true in the kind of middle, in the Gulf Stream kind of area. So there's a bit of both going on there. It was a bit inconclusive. I think.
If you think of what's happening in March, through the other winter months, December, January, and February, you've always got strong heat loss to the atmosphere.
Right.
And then in March, then it suddenly changes. So some years you're going to have strong heat loss, and some other years you might get weak heat gain. If we're trying to find a reason why March is special,
Yeah.
there's a strong transition at that time in the radiation in the atmosphere couple, and that could vary from year to year.
Right. That would suggest that March should be less sensitive, would it, to the ocean?
I don't know if you could talk about
yeah.
afterwards, but you could think that in the core winter months that there's very strong coupling, so you don't get strong variability. It's always in a
Right.
state. So when that coupling breaks down in March, that might cause you strong variability.
Okay. Yeah.
So yeah, there's lots of people asking questions. So any more? Next question. I'll go to the back of the room maybe to give them a chance. David.
Yeah, very fascinating story. Following this up, you showed that actually not the peak of the variability is not just over the whole March, but you showed that the daily change. So it's actually very, very narrow. And it showed on the first slide, you showed it might be just the peak just a couple of days mid-March. So all what's special about mid-March, and from my point of view, okay, this is where we have the maximum sea ice extent, where this can play a role in the reasons for this.
Right. Okay. So the question was, well, when you look on the daily timescales, it was very strongly peaked, and that at a time where you have maximum sea ice extent, and that can be playing a role. So, first of all, when I showed the daily, it was 31-day running means over the course of the year. So each point was really a 31-day mean centered on that point. So it wasn't just 1 or 2 days. But it's true that sea ice could be playing a role. I guess that's another possibility. Yeah, I have not looked into whether the Decatur prediction large ensemble. Yeah, it could be. I guess it's hard to look at because you don't really have the observations going that far back. But it's a possibility.
Okay, so I think we've got time for a couple more. So Doug is desperate there to ask a question, and then Alex, do you still want to ask one as well? Okay, Doug.
Yeah, thanks for an excellent talk. So a lot of what you've shown up is consistent with what you find in seasonal time studies with the signal paradox. And it's really that the jet doesn't shift enough. So I wonder if that's the case, then I think you might see some skill perhaps in the wind, but not in the extreme positions that you're looking at. Do you see the correlation map or skill for the wind? Do you see any skill anywhere in that region that is not in the box picked out? In other words, the jet's not shifting into those regions in the model, but it is doing something that gives you some skill. Yeah.
Okay. So the question was whether the model might have skill in other regions of the North Atlantic, but not in the region that I focused on because it's not shifting properly. And there were analogies with the signal to noise paradox that's been seen in higher frequencies. And I definitely think there are analogies there. And I feel like our models are missing something. They're not responsive enough to things. But I haven't looked at maps of the correlation, but I have looked at whether any grid point in the North Atlantic has the variability, the degree of variability that we've seen in our observational record. So not just focusing on that box, just looking anywhere, and none of them do. But yeah, that would be a good thing to look at, is a map of the correlation between, like the Met Office has done, I guess, with their regions where it's the signal to noise paradox is present.